All right, good morning, everybody. There's three of us right now, so I'll stall for a minute or two, give anyone else that intends to join the opportunity to do so. I just turned on the recorder, so you don't need to remind me to record the meeting, and then shortly we will begin. Today's stated topic is the hydrologic cycle and a little bit of discourse on data sources. And then, because I don't think that's going to take the full hour and 20 minutes or even a full hour, we're going to do a sidebar on some data analysis in preparation for the exercise set that you have coming up. I need to show you how to measure areas from just a digitizing tool, and then how to accumulate, deaccumulate data files. And everybody races to get their video turned off. I'll leave mine on. And that will conclude today. And then tomorrow, when we talk about watersheds, we'll spend some more time in actually using the digitizing software. Yesterday, I was preparing tomorrow's demonstration lesson because it's also part of the homework. And the software I had put up there that I intended for everybody to use works, but it doesn't work correctly. And so the cop-out that I take in that case is just to delete it and install something else. So we're going to use a different tool than what I had originally intended. I've decided to leave the pre-recorded videos alone, but I will state right now to y'all that the GAGE software, which was a digitizing and measurement tool, is not functioning correctly in the shared workspace environment. And that is unfortunately one of the downsides of using free software, is that over time it starts to break because the machinery changes, the operating system changes, and the software doesn't. And building these things from source is really, that's hard. So at some point when it breaks, it's unmaintainable. And I think Engage, at least in my computation environment, has reached that. So I have 5 of y'all, and I'm going to slowly go ahead and start. Yesterday, it turned out lesson 3 wasn't working correctly, and it wasn't giving people multiple shots at it. As far as I know, that's been repaired for the entire class. But if you encounter that on any of the future lessons, go ahead and email me right away, because that's a failure on my part to do a setting correctly. Unfortunately, I can't batch reset it, so I have to manually do it. It's not that hard, but I just need to be told. Because I have no intention for the lessons to lock you out after 1 or 2 visits. I want you to be able to go through them as many times as the computer allows. It allows up to 10 revisits, which should be plenty. And then remember, all the material is in the content sources. So I'm going to go here now on purpose to be sure it's still working. Excellent. Lesson number 3, hydrologic cycle. And let's see what's there. There's the PowerPoint, which we're going to look at shortly. There's no data. And there's this poly area spreadsheet, which kind of doesn't, it kind of goes with the next lesson. But that's a good thing it was there because it reminded me of something. And there's no localized video files. And then the reading is currently blank. That'll change over the next, by the end of today, because I'll cross-link all the readings. So with that, let's begin. So I've already downloaded the lesson content, and with any luck, I'll be able to find it. That's not where it is. What are my other choices? See if that gets me to the right one. There we go. Module 1. This is 3. And so the First part of this, I'm going to read stuff to you that I take from Bruce Hart's book, and the second part will visit some different data sources, and the third part will be how to analyze that data, not necessarily actually do it, but some of the preliminaries that we have to do, and a little bit of a R scripting review. So the topic's the hydrologic cycle. Hydrologic cycle is classic. Any textbook, pretty much any user manual has some hydrologic cycle. So here's a drawing of my interpretation of it for the purposes of discoursing on it. So most of the hydrologic cycle drawings all kind of look the same. They might be represented different. They might have block diagrams. But there's these arrows that represent transfer processes. So this one right here that the cursor's moving on, for instance, is labeled evaporation, and it's coming from this lake or stream. And so it's representing the process of water from the lake or stream evaporating and making its way up to the clouds. Same here for the ocean. And then these are just labels of surface water bodies. And then here's the groundwater flow. So everything beneath this dashed line is representing the groundwater system, which is not the topic of this course. There's another course on groundwater, but the two are related in that they interact with one another. So here's the groundwater flow in this drawing, moving from left to right, making its way out to the ocean, and eventually back into the clouds. I have mandatory trees right here and here, which are transpiring their little hearts out. And you have to bear with me. I mean, that kind of looks like a conifer, which are genetically engineered by the tree gods to not transpire very much because water is a shortage for them. But they're a lot easier to draw when you make a drawing. So these are drawing water from the soil. It's being used in the biological processes of the tree, and a fraction of it is pumped from the soil through the tree back into the air. And that's called transpiration. And in surface water hydrology, when we're quantifying things or attempting to describe process models, transpiration and evaporation are usually lumped together because there's no convenient way to split them apart. It's even difficult to make measurements of one or the other. These arrows here represent the return of water from the atmospheric system to the surface system. Here is showing precipitation, and generally when I talk precipitation, I usually mean rainfall. I have not in my career dealt much with snowfall or icefall. There are conversions that say a certain number of inches of snow that has a certain density can be converted to an equivalent depth of water. And as that becomes necessary, we will invoke those relationships. So from Bruce Hart's book is this paragraph, and I think it's worth reading. So the water cycle, also called the hydrologic cycle, refers to the pathways of water in nature as it moves through its different phases, through the atmosphere, down, over, and through the land to the ocean and back up to the atmosphere. And he even got it right with this word phases, because in groundwater or in surface water, the water phase is liquid. It goes into the gas phase to get up into the clouds, moves on shore. Precipitation is a good name because that gas coalesces onto a precipitation nucleus and changes phase from gas again into liquid, and then falls from the sky. And if it's cold enough, it actually goes all the way to the solid phase and falls as ice. And I think that's what I just described right there. As the precipitation continues, part of it may flow over the surface in the form of overland flow. So it's shown here as surface runoff. Part of it enters the soil as infiltration. So a fraction of this precipitation becomes runoff. The remainder another fraction becomes direct evaporation. And the remaining fraction is infiltration, which in this diagram there's no arrow for. The surface runoff collects locally in puddles or small ponds as depression storage. So depression storage is actually pretty important, and we will examine that later on when we're looking at the two software tools on how either of them handles that particular store in a hydrologic modeling context. The other storage is actually storage on the leaves. I don't know if it has a particular name. It's called canopy storage. And in Lubbock, canopy storage is probably a real thing, but it probably doesn't matter very much. I mean, Lubbock is clearly dominated by precipitation and evaporation, and then whatever infiltration there is. And canopy storage is going to be less substantial. Depression storage is not. I mean, we have playa lakes whose purpose in life is to store water so that the ducks and geese have something to swim in. Okay, so it gathers in small storage elements or in gullies and larger channels, or ultimately becomes stream flow, which makes its way to a lake or the ocean. So that's your typical representation of the hydrologic cycle. Bruce Hart goes on to talk more about the infiltration, and so this shown here is these wiggly red arrows. And the drawing, I thought the drawing rendered better than this. This arrow is not pointing up. That one's pointing into the wiggly thing to get down into the groundwater. I've also superimposed an idealized hydrograph picture. So the hydrograph is measured when it gets into a stream. So there's no forcing input, and the stream flow is slowly declining over time. If we have this component, which is called base flow, that implies that there is groundwater connection to the stream. That's not always true for all streams. And then there's some forcing term. Think of a substantial rainfall event that causes that stream flow to rise, comes up to some peak value, and then it declines as the event passes. We'll study this diagram more later on. The infiltrated water can flow rapidly through the soil layers and exit into springs or streams, percolate more slowly into the groundwater, and eventually gets to the surface system. There's a portion of infiltration that stays in the soil profile by capillarity and other factors, and that's the portion that's available for plant uptake. It's not big in individual magnitude, but it's important for vegetative processes all over the world. So the fraction that becomes soil water is really important from a societal point of view. And here's the idealized hydrograph that I said we'd visit later. I'll let you read that part on your own, because that will use up the hour. So the geological formations form pores, and the water is stored in the pore space. And then there's this concept of water table in the case of an unconfined aquifer. And then the portion that's not aquifer, but is soil that stores water is called the Vados zone. And it's commanded entirely by a Star Wars character known as Darth Vados. Stream flow is fed both by surface runoff, so that's direct flow from a rainstorm, for instance, and subsurface flow from connected aquifers. The stream flow that results from groundwater outflow is called the base flow. And in this diagram here, the base flow is shown as this purple region. And in the absence of storm flow, referring to the diagram again, base flow might follow this purple trajectory. So it's declining over time because the groundwater store is slowly being depleted by the stream. And in this particular diagram, perhaps it would follow this path. It wouldn't rise up like that, but it would follow that path and reconnect out here somewhere. So we'll pretend that that's the base flow path in the absence of storm flow. Then when there is a storm flow input, we get water that's directly from the storm flow that causes this rising limb and a trailing limb. But this little portion here where it's starting to ramp up again with respect to base flow, that represents what little recharge occurs during the storm event from infiltration. And it may be more substantial than in this diagram, but you get the point. Base flow is important for larger basin scale studies and long-term hydrologic description. So short-term event stuff that's often handled in engineering hydrology, or at least localized flood, street flooding. You're trying to explain the behavior of a subdivision in order to construct detention ponds. There may be base flow component there, but it's pretty irrelevant because of the time scales involved. Base flow is a longer time scale process than the peak flow and recession limb. And this is all spread out in this diagram so you can see the different parts. When we later on look at what real hydrographs look like, they're all spiky like my hair looks right when I wake up. There's multiple peaks over a relatively short time period, matter of hours, and this idealized one rarely exists with real data. And then finally, the hydrologic cycle, at least in this story, is closed, or the cycle is completed through the evapotranspiration process. And we discussed a direct evaporation and then the transpiration process by vegetative cover. And we'll have an entire lesson on evapotranspiration, although we're not going to get deep into the process, but we'll examine a few of the process concepts that are used in practice. And then here's another diagram of the hydrologic cycle. This one I took from Broussard's book directly. And what I have is I have rows of ellipses around the process that are important for surface water hydrology description. And it doesn't mean these other ones are unimportant, but we're going to be very interested in behavior precipitation, either from a data analysis point of view or from a design point of view. Infiltration matters. Interception, depression, storage, I kind of have them lumped together, but they're a short-term store of water on the surface. The base flow and stream flow component are going to matter, and evaporation is going to matter. And our two tools that we're going to get painfully familiar with, HEC-HMS and SWIM, have specific process models for all these processes. And they don't have one process model for all the processes because that would be too easy. They have 9 or 10, and you have to choose it. And we'll discuss when we get to that, making those choices. So to condense those pictures into just a handful of fundamental processes, the processes we have are precipitation, and that I consider an input or a forcing process. We have loss processes, which are evaporation, infiltration, and storage. And by losses, if you think of the precipitation as a signal, radio signal, cell phone signal, you lose a portion of that signal to evaporation, infiltration, and storage, and those losses occur on the watershed. And then what's left is runoff. And oftentimes that's what we're concerned about, is the input and the runoff. And we want to quantify the losses, but we may not actually care in which category they are. So from your undergraduate hydrology class, you may recall the SCS curve number method. It's not specifically a loss process, but it mimics one. And in that, the curve number was a way of representing everything in this green box. And the curve number would convert the blue box to the red box via the green box. And we didn't concern ourselves in the curve number method much with which of the processes was doing the loss work. Now we'll take a short tour in hydrologic data. Amazingly, there is a lot of hydrologic data globally. Unfortunately, there's not a single website one can go to get all the data that you want. Much of the time, the data you want actually exists, so that's kind of good. but the individual databases are not structured the same way. So a portion of a hydrologist's time is spent not so much acquiring data as converting the data into a uniform structure for whatever their needs are. So let's start with rainfall. Some sources of rainfall are the National Weather Service, and this one looks just like Office of Climate. So this is they call them landing page. This is a landing page for National Weather Service observations. And a lot of times on the National Weather Service website, I find it reasonably difficult to navigate. Not hopelessly, but a lot of times I have to poke around until I can find what I'm looking for. The irony is I know it's there and I've bookmarked it, but governments like professors at universities, they move junk around all the time to justify their existence, remind themselves they're still alive. So if you ever found something in National Weather Service and you go back a few weeks or a few months later and it's gone, it's not gone. They just moved it to someplace you can't find, and you'll have to be persistent. And we'll visit one particular thing in the National Weather Service shortly. The other one that is often overlooked is something called a surface weather observation station. Every airport in the United States, and probably in the world, at least in the world major airports, have a weather observation station. These are important for the actual aviation industry because localized weather is kind of crucial to make this big old bucket of bolts and plastic and wires fly in formation and land in formation without falling apart and strewing stuff all over the countryside. So the couple things that are important for the operation of the aircraft is something called density altitude. To determine density altitude, you have to be able to measure temperature, relative humidity, and barometric pressure. So density altitude is the altitude that the plane thinks it's operating at based on the air's ability to hold it up in the sky. As an example, Intercontinental Airport in Houston, Texas, I think has a topographic altitude of maybe 100 or 120 feet above sea level. It might be higher, it might actually be less. I distinctly remember landing there in about 2003, and it was 105 degrees Fahrenheit at the time of landing. The density altitude of the airport at the time was something like 9,000 feet. So the airplane was landing at essentially sea level, but it had the equivalent lift of being 9,000 feet in the air. And so we were landed on the shorter runway, which is 10,500 feet of runway, and the aircraft had to use the entire runway to get slowed down enough to find its way to the gate. It was an unusual flight because that flight left Boston Logan Airport that morning, and it was 20 degrees Fahrenheit. So it went from freezing to being in the middle of an oven in less than 3 hours. So I guess I'm lucky that the plane didn't spontaneously disassemble at some point. So that information is provided by the Surface Weather Observation Station. So what they measure, or they record every hour, they record rainfall, temperatures, incoming solar radiation. This kind of looks like a evaporation instrument, but that's measuring wind shear, and they measure wind speed at some different elevations. So that data is often overlooked. It's publicly available. I don't actually recall the website. Whenever I need to use it, I just Google surface weather observation stations and work my way through that. Oh, I didn't know someone else was waiting. Superrata, as you join us, I apologize. Fortunately, this is recorded. Good. Moving forward. This picture's out of place. So this should be back with a hydrologic cycle picture. I like this particular one because it's got all the bits and pieces that in a surface water computational hydrology context, one might want to ask questions about. And they're using the wiggly line to represent different processes. They're using the lightning bolt to represent rain process. That needs to get moved into a different part of this presentation. Moving on with hydrologic data, there's also, in many metropolitan urban areas, local gauge networks. And I have a picture of one for Harris County. And this is somewhat old. I think this is probably 2010-ish, so I don't even know what the interface looks like today as of right now, but we can go visit that. And in this one, these little square boxes represent rain gauges, and actually in this particular network, there's also a stream stage gauge. So rainfall and how deep the water is located in each of these boxes. And then a public user, just a regular citizen, can go to the box near their area and it returns various readings, and then they can export the files for hydrologic analysis work. Generally what a analyst would do is export the files for every gauge and then analyze them. So that gets kind of big. I mean, there's, at the time of that photograph, I think there were 116 gauges. I believe there's more now. For STREAMFLOW itself, there's some other sources of data. By far the most commonly accessed one and probably most useful is the National Water Information System, NWIS. It's operated by the United States Geologic Survey, but if you Google NWIS, you almost always will get to the right place. There's a few other I've shown here. IBWC, International Boundary Waters Commission. So that would be appropriate on the Texas-Mexican border if you need STREAMFLOW data there, especially if you need some older data. And then the often overlooked paper-based records. So this bullet item is fast going away in our lifetimes because paper's evil. But there are quite a bit of paper-based records that have never been digitized. So I guess my message to y'all is, as you come across paper-based records, if you can't find them electronic, you kind of owe it to the rest of the world to at least scan them into a PDF file and put them in a public website somewhere. And then the local gauge networks can often be inferred to generate STREAMFLOW information. So here's an example screen capture of the USGS website. And this one I went through NWIS. So there's a couple ways to get to it. Every state in the U.S. has something called a water, I can't remember what it's called. There's like a water resources information center for each state. So Texas has one, other states do. That's one way to get to it, and it'll redirect you to the main website. The other way is through NWIS. And let's suppose that you wanted to get some historical observations. The way to do it is you're going to select the historical observations or current conditions, but you're building a query. You're actually querying a database. You don't have to know much to do that, but if you put in Harris County and Buffalo Bayou, it returns a few choices. In this case, it returns this particular station. And once you select the station, you get information on what's actually available. So on that particular station, we have peak stream flow, annual statistics, monthly, daily, and it gives the date range, and it has the count of records. So records count is how many actual observations are contained in the database. And you all see the word provisional, so that's government speak for this is the data that we're serving publicly, but if somehow you do something with it that causes monetary losses, it's not our fault. And I just picked a particular peak file and It's important to look at these because the files themselves initially at first glance are a tad confusing. Up here at the header is, there's more header that I'm not showing. It has gauge height identification codes. And so this is gauge height code, AG gauge height code, and it is referring to this column right here. And in case of these data, the gauge height code, the AG height code are code 6, and then C, which I think I probably edited the list. So they use numeric and alphabetic codes. And what code 6 is telling me in this particular file is that these stream flows are in urbanized and regulated watersheds. It means that there is a impoundment that impounds water that's collected from over, I think they use 15% of the entire watershed area. That has some significance later on in flood frequency calculations. When we get to the peak FQ software later in the class, we'll see these codes visit again. But they still record gauge heights, which is this last column, and should have peak discharge. I'm pretty sure these are these columns. So in 1984, on July 18th, at gauge 080-73600, the peak discharge for that year was 1,940 cubic feet per second at a observed gauge height of 53.12 feet above the datum, which I'm pretty sure is mean sea level. You'll notice also in 1984, on October 25th, there was a reading of 3,340. And at first glance, it's like, well, these are annual peaks. How can there be two annual peaks in the same year? In their infinite wisdom, like all government agencies, they don't count years the same way grown-ups, humans do. So they use something called a water year, which runs from October to September. So the beginning of the water year is October, the end of the water year is September, and it spans calendar years. So for example, water year, and I can't remember which one if it starts at the beginning. For the sake of argument, water year 1983 includes July of 1984. Water year 1984 starts in October of that year and goes to September of 1985. So that's why oftentimes you'll see two calendar years in the same data file when we're talking about annual peaks. Obviously with daily data that becomes unimportant. So for example, in this thing, 94 has two peaks in the same calendar year, but those are different water years. And the water year is October to September. A federal fiscal year, I think, is also October to September. A state of Texas fiscal year is September to August. And different states and different organizations use slightly different fiscal years. That's pretty much job security for accountants and people that deal with fiscal years. So if you can't make it this engineering science gig, if you can handle fiscal years, you have a good employment future. So these gauges, if you will, there's different kinds for measuring stream flow, just as there's different kinds of rain gauges to some extent and a few other things. And so we're going to spend a little bit of time here to discuss different kinds of gauges. The first is a continuous record gauge. And usually what gets measured is stage, or how deep is the water. And then with any luck, we located as something called a control section. A control section is hydraulically a section in the stream where we're pretty assured that the water has to pass through critical depth nearby. And the reason critical depth is critical, pun intended, is that that gives us a one-to-one relationship between how deep is the water and what's the flow rate. A second type of gauge that's also in common use is something called a CREST-STAGE gauge. And all it does is measure how deep the water is, and it does it in a forensic context. I'll show you a picture of one shortly. They're not mechanically very complex, but they only do one thing, which is to record how deep the water was at the last deep water event. So a hydrographer has to visit the CREST-STAGE gauges pretty much normally done after a fairly large event, survey the debris line because that's used as an independent check of the flow estimate. So here's a continuous gauge, and DCP is USGS speak for something called a data collection platform. So it may literally be a platform floating out in the water. Oftentimes you see a little vault box on the side of the highway near a bridge. And those are the data collection platform. So a continuous gauge works something like this diagram here. This is pretty obsolete. There's different technologies that are used now. But a lot of the same principles are engaged. That there's a connection from the stream to it's called a stilling well. And the stilling well then has a tool that measures how deep the water is. So this is showing a float gauge. I would hazard a guess that we don't install float gauge systems anymore. We maintain the historical ones because they work well. There's no point in breaking them. What they're replaced with nowadays is something called a Butler gauge. And so there's a line that goes down here to the bottom of the water surface or someplace where there's a surveyed elevation. And then there's a machine that pumps gas through that line at a known pressure. And depending on what the water surface is, the mass flow rate changes with that ideal gas law. It's basically a Pivnert bong. And it records those pressures. Those are converted to water depth, and that's how it's done now. The machines themselves are pretty simple when you rip them apart, but they have very expensive looking electronics in them. And they are designed to interface with a satellite transponder or transmission radio. They get beamed up to a satellite. They're done as bursts, so they don't beam continuously. They basically store data locally, and then at their satellite window, which is pre-programmed, they get 15 seconds to push all their data up to the satellite, and then it goes to the satellite, comes back down to an Earth station in Maryland, and the smallest federal agency in the entire government collects and then organizes that data and puts it out on the public service. Last I heard that, I can't remember the agency's name. It's 4 people. It's a 4-person agency. One of them's a supervisor, so it's 3 actual working people. Bunch of computer geeks like myself sitting in a room. They have M&Ms are piped in every few minutes to maintain their blood sugar levels, and they manage all this data coming down from satellites. I have this photograph here of a staff gauge. It's general practice that some kind of staff gauge is always near the data collection platform, and when the hydrographer visits the site, they make a staff gauge reading and they record it in a ledger that's kept inside this vault box. And that staff gauge and then the electronic reading are from time to time compared, and the staff gauge is used to collect the electronic readings. Because one of the wonderful benefits of electronic anything is the instruments tend to drift over time. And the staff reading can be used to correct for drift. So never overlook a staff gauge. They're actually remarkably useful. And to my knowledge, I don't think anybody's gone to the trouble to make an image interpretation software package to actually have a camera look at a staff gauge and just record those readings that way. A colleague and I have experimented with that. We can even get them to work in the dark, but they're just not as reliable as these things. Maybe someday in the future that image interpretation software will be a lot better than it is now. And then the conversion from stage into flow rate is done by a technique called stream rating. And this diagram illustrates how stream rating is done in a conceptual fashion. So a particular stream, a tagline is pulled across the stream. It doesn't have to be a physical tagline. It can be electronic using global positioning system, which is pretty much how it's done now. And the stream is divided into subsections from across the stream. So this one has 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18, that's not bad. In general, the goal is somewhere around 20. And the reason being is that each subsection represents roughly 5% of the stream width. Not necessarily stream volume, but the stream width. And then a instrument is taken to a particular subsection. Readings are made at different depths in that subsection. Each reading is done for 40 seconds. And then the product of velocity over that 40-second reading and the area represented by that subsection, so this darker blue area in this drawing, produces a discharge, or how many cubic feet per second are going by this subsection. And all those discharges are added together to get a total discharge. And the areas, which you have to know to make those calculations, those are added together. And total discharge divided by total area produces something called a mean section velocity. And that's useful for flow quantification. And then the individual velocities have value to see where most of the flow is occurring. The depths that these readings are made is specified by how deep the water is at some instance. And there's a few different averaging formulas depending on whether you're making a single depth reading. And I believe a single depth reading is made at 8/10 of the total depth up here somewhere. A 2-depth reading, which is, can't remember the numbers on this, 0.6 and 0.2, and then a 3-depth reading are the more common ones. Making them beyond that with physical flow measuring instruments is not practical because of the time involved in each station. Now this process has been modernized in that instead of putting a little propeller at these 3 different elevations, an acoustic Doppler velocimeter is used. It sends sound signals down, and from the frequency shift in the return signal, the velocity can be computed. And because it's electronic, it can actually shoot a bunch of depths, not simultaneously, but really fast. I mean, milliseconds fast. And so they can, nowadays we can actually directly integrate this entire subsection, in which case you're getting the velocity at every depth. Not every single depth. It uses a technique called binning, as in the same concept as a bin that you see in histograms. And the bins are a couple of centimeters tall, and it adds up all the behavior in the bins. So this is glorified integration. And once that discharge is computed for the stage, you're done with that rating, and then it goes back on a different day and time, presumably when the stage is higher, and makes that measurement, and those are all stored. So what's going on here is the stream gets rated at every different stage. Now, not every possible stage, because that's also not practical. But maybe when the stream flow is really low, they go out and rate it. And maybe when it's typical, it gets rated. And maybe when there's a teensy-weensy flood, it gets rated. And then when there's a really big flood, it gets rated. When there's a huge flooding, they don't put instruments or people out there. You do the debris line after the fact. And all that information is put into something called a rating curve. And here's a diagram of a rating curve as a curve. Now, realistically, these aren't stored as pictures. They're stored as depth discharge ordered pairs in a computer program. But the curve can be constructed from those pairs. And just reading from the USGS website, the continuous record of stage is converted into stream flow by applying a mathematical rating curve. So a function that represents this blue curve is used to convert stage into discharge. And the computers use these site-specific curves to convert the water level to flow about the river. Rating curves are not done as a one-of thing. They by design get adjusted over time, especially if you get up into these deeper, rarer occurring occasions. So maybe a stream is first rated on 5 or 6 different stages, and then a couple years goes by and there's 11 more. So those 11 get added to the initial 6. Now you have 18 points. So the curve is refit through the 18 points. And this is an ongoing process. After a lot of points, the refits don't change very much. So the older a rating curve is in a relatively static stream, the more fixed in time it becomes. And so, for example, that Buffalo Bayou one, that's been having flow measurements in it since at least 1920. Those rating curves aren't going to move much unless there is substantial change in river geometry. And on other kinds of streams, like ones around here at least around Lubbock, I've rated a few for some research work, and those have stream channels themselves that actually move all the time. There's nothing more unnerving than wading a stream. So I'm up to my waist in water with my flow meter, which is an elaborate computer thing. It's got wires and little fingers, acoustic Doppler flow meter. And we're trying to make single point readings, so it's a single depth. So you measure how deep the water is, and then you want to set the depth gauge to 8/10 of that depth. And they have a mechanical calculator built into the instrument to make it very fast to do that. But because the stream bed was moving so much, you could feel it moving under your feet, it would get deeper during the 40-second reading. So what you had to do eventually is we had to guess how deep 8/10 was going to be at the end of the 40 seconds, set the height for that, put it in, and you just let the instrument slowly sink into the stream. It was really a spooky feeling. It's the weirdest thing I remember in stream gauging, because I'd come from California before that, and I was used to streams that had gravel bottoms, and they didn't move. The only thing that was moving was the fish that was biting your toes, and you're going, why am I wading a stream when I could be catching a beautiful fish? Moving on, CREST-STAGE gauge. So here's a photograph of a CREST-STAGE gauge. There's a lot of these in Texas and actually all over the country. They're pretty easy to recognize. Just visualize a pipe bomb that's attached to a wing wall on a bridge. And as long as there's no ticking device or a fuse burning, it's probably not a pipe bomb, but they look just like a pipe bomb. And I bring that up because a few years back I was tangentially involved with a study, and the county we were studying is Concho County, and the county sheriffs and engineers kept pulling these things off the bridges because they thought they were pipe bombs. And it took a lot of phone calls and a few face visits to tell them how to recognize a stage gauge. We had little stickers on it that said it was a research stage gauge, but as the sheriff said, he said, well, that's, if I were a terrorist, I would put a sticker on it to try to keep my deputies from tearing your bombs off. Ultimately, the problem got resolved, and they're still in service today. So it's a vertical pipe, and there's holes drilled in the bottom. And not willy-nilly. These are done by precision machinists drilling holes on galvanized pipe. I'm sure they laugh when they go home in the evenings. I can't believe I was getting paid to drill holes in a stupid pipe I can get at Home Depot. And then inside this, so both caps are removable, but the bottom cap is drilled so that water can get in and out, and then the top cap is left undrilled. There's a piece of wood that's put down this pipe, and it's a piece of redwood. It comes from a single lumber yard out in Northern California somewhere. And then they've been using this particular redwood from that lumber yard for probably 80 years. And so the redwood has to meet a particular standard. And then there's a cork, just like a wine cork, but it's ground up into a very, very fine flour. It's not just cork granules. It's really fine. Flour is the best analog I can come with, and that's put down in the bottom here. So as the river stage comes up, that cork floats up to however high it gets, and then the river goes back down, and there's a residue of cork that's left on that piece of redwood. And then the hydrographer comes out from time to time, opens this cap, pulls the redwood out, makes a pencil mark at the last height, and puts a date on it, and then carefully cleans the cork off, puts it back, and then puts the wood stick back into the sleeve that's formed by the stage gauge. And the elevation right down here is carefully elevation surveyed. And so when putting the stick back, there's quite a bit of care to be sure that it's seated correctly in the bottom to get the to be sure that it's measuring at the correct elevation. So this is done for a particular sampling interval. So it's not only collecting the highest of a particular water year, it's also collecting all the high marks from the last major releveling. At the end of a water year or a observation period, then all those elevations are recorded, and the stage is then known. At the same time, they're resetting the wooden pipe, the wooden stick, so that's done pretty quickly. Then a elevation survey of debris lines, if it's available, is made. And the slope area from either debris line as well as from the staff gauge can be used to estimate discharge in that stream during that crest. It uses Manning's equation. So what we get from the crest stage gauges is we get the value for slope. The stream by this point has been elevation surveyed, so the cross-sectional area is known for any depth, and the hydraulic radius is fairly straightforward to determine from that known area and depth. Manning's equation is applied, and a discharge is estimated. So after a few visits to a stream, the only really unknown thing would be Manning's N, and that would be it. But over time, that becomes fairly straightforward to quantify. So after the first few measurements, maybe the first 10, this won't be terribly reliable. But as time progresses and you get a better handle on the roughness coefficient, and even though these are done with stage gauges, there's also a separate measurement called slope area that's done by surveying the debris line. After a few hundred of these, this becomes a very reliable way to estimate discharge, peak discharge at these locations. And we could go look at a tool that does it. I want to see if it's actually working. So if we know Manning's End for a stream, and we know the cross-sectional area of flow, let's suppose it's 100 square feet. We know the wetted perimeter for that 100 square feet. I'm going to make up a number. Let's make it a pretty shallow stream. And the dimensionless slope would be the difference in elevations at the two crest stages, or it would be the known topographic slope of the stream bottom. So I use 0.5%, and then it just does the calculation. So for those particular conditions, it gives a discharge of 56 cubic feet per second. So I was making those numbers up. So that's a really small hydraulic radius. That'd be a very shallow stream. And there's no reason to use this particular web interface. This is a very easy calculation to make. But that's what goes on in stream rating. And that almost concludes the presentation in Dallas-Fort Worth region. I thought provided me, there we go. Okay, so a colleague of mine sent me these links. So here's an example of some of the data that is relatively available that's relevant for hydrology. There's historical climate data, solar radiation. So these are the ones that, why she sent me this. I was looking for this kind of data for the evaporation part of the class. But in addition, there's the USGS gauges. We'll go take a look at that. Hopefully it will spawn a new site. This looks like it's some sort of geographic interface. They use the, yeah, this is a map server. And so it has data for these sites. Tells you the site number, what kind of flow it is, what kind of data it is, and then you get the access thing. And that should look very familiar because that's now, we're now into the NWIS database. And let's get some monthly statistics for that site. I'm just going to take the see what happens. So here's discharge and gauge height. So in January, the gauge height's around 7, and gauge height of 7 feet produces around 60 cubic feet per second. Let's see if we've got anything that's bigger than 7. Well, this is a really boring gauge. 6.76 is the lowest, so we would expect that to be less than 50 feet if it were a critical section, but it's not. Actually, there's this one measurement here is probably incorrect, as is that, but who knows. So the rating curve is what's used to convert this bottom table into the top table. So it's not surprising that the one-to-one relationship does not exist for this gauge, and for many others it doesn't. So they're done by rating curve, and that eliminates the need for having to have stuff at a control section. But if you're designing your own monitoring program and you have the ability to put something at a control section, that's what you want to do, because then the rating is simplified. Okay, hopefully, no. So that was the National Hydrography Database. You can actually download the products. If we need a digital elevation model, which is useful in watershed analysis, we can go to this site and it gets you to a standard governmental useless information page. And it has a listing of the different products. And this one, just by the title, you would need to have a geographic information system to make any use of the data. So either SRE, ArcGIS, or I would imagine that Quantum GIS would work, which is free. And then moving on, web soil survey, which we will see tomorrow in some detail. This actually goes down into, we'll go to the landing page tomorrow, because the landing page, in my opinion, is the most difficult to interpret page of any government website I've ever been to. But here you would go to your location of interest, draw an area of interest, it pulls a map, and then from there you can get some other data. I'm going to study that tomorrow. And then some other sites, and then if you're dealing with Dallas-Fort Worth area, so Monica, myself, and a few others, we've been working on some project work there. So that's why she sent me that link. So that gives us a pretty good introduction to the kinds of data that are available. So that's it for this presentation. It took longer than I thought. So I think I will leave the building the integrator and doing the data analysis relevant to watersheds for tomorrow when it's supposed to happen. Are there any questions that you all have? Okay, silence, that's okay. Hopefully you all heard me. Okay, well that concludes today's lecture part of the lesson. I want to take a visit at the exercise set to be sure that I'm hitting what you need to do to be able to do it. Otherwise I'll have to change the due date. I'm fine with that if that's necessary. Okay. Why is it going into the... Okay, so can you go to the internet? Yes, you can. You all can do that. So problem 1 is not a challenge. 2 and 3, you would use Chow, Maze, and other to get the actual information you need. Those are contained in tables in that book. 4 is very much like the quiz 1 problem, as well as I believe an example that was done yesterday. 5 is a little trickier. The first line of this worksheet is done for you, so essentially you have to fill in the different columns in order to complete the table. And then in quiz 1, I believe it asks for a specific row of this table. So if you do this before quiz 1 is a lot easier. And number 6 is what we need to deal with tomorrow. Number 6 is going to be your one and only hand delineation of watershed. I feel that it's important to demonstrate to yourself that you can do it by hand if you have to. By far, this is no longer the preferred way. We have machines to do a lot of this for you, but sometimes it's the only way, especially on really small watersheds. It's often quite a bit faster. So here's the outlet point. We're going to draw a watershed on this, and we're going to make some measurements. The important thing in this diagram is this is 1 kilometer, that linear distance. And I need to check my data. I think I have actual observations for this location. So we will be revisiting this watershed repeatedly throughout the course. And I will show how to do that tomorrow. The the tools that for doing area and length that I had intended for y'all to use doesn't work. So I'm bringing another tool. I've already installed it in all the shared hydro sites, and it appears to be running. I'll be testing it this afternoon to be sure it works correctly. And if you have GIS, the latitude and longitude in degrees, minutes, and seconds of that riser pipe, that red circle, is 31 degrees, 18 minutes, 31 degrees, 18 minutes, 19 seconds north, 99 degrees, 7 minutes, 52 seconds west. If your software can't handle degrees, minutes, seconds, just remember that there are 60 seconds in a minute. You can convert that to degrees and decimal degrees pretty easily. Okay, that's all I have for today. If there are no questions, oh, I lie. I tell a lie. I want to go through this very quickly because this will have relevance for tomorrow and for some future stuff. And we'll see this again. The kind of data that we deal with, which is rainfall, runoff, and to some extent even topographic data, are usually represented as discrete samples on a continuum. So we don't actually get continuous readings. We get them at different points in time. And so the results can be represented as a series of pulses. And what we need to do oftentimes is convert from pulse to an accumulated format. So we have these red pulses here, and we want to integrate that red function to produce this blue function. And it's called a running sum or an accumulation. Oftentimes we also get the accumulated, the blue function, and we want to convert that down to the red function. That's actually more straightforward than it sounds. The cumulative space is often how rainfall is collected. It's collected in an accumulator. STREAMFLOW is usually collected in increments. And so initially the two data streams are incompatible, although they actually are compatible with a little work on our side. And so accumulating the increment is just aggregating or ordinary numerical integration, and then differencing the cumulative is called disaggregation, and think of it as numerical differentiation. So with those two concepts in mind, moving between the red and the blue and back and forth is straightforward. And here's just a simple example. So suppose we have incremental depths here in this column. We have 25 readings, and we want to get the accumulated depth. So you can think of the incremental depth occurs at the end of the reading period. And so here we're adding up the amount that was accumulated during the period to what was there before. So it goes from 0 to 0.121, 0.242, and so on. And that produces the red curve. And we'll look at some, we'll look at how to implement that in an R script working on an input file tomorrow. So now I am done for today. One last shot at questions, and then I will terminate the call. Okay, I have one important question for you all. Was I loud enough during today? Because I'm kind of hoarse today. Something in the air is making me hoarse. And I had some allergy pills this morning, and it really dries me up. So were you able to hear me?
Yes.
Okay, thank you. Oh, thank you, Suvarana. Good. All right, that's good for today. Then I will disconnect it. The reason I ask about being able to hear me is if I know it's weak, I can attempt to boost the signal when I make the render the recording. Oftentimes that's usually a disaster, so I won't try unless it's a bad recording. So everybody have a great afternoon. You maybe want to take a look at exercise set 1 now, because you could, if you had time, do most of it right now except the last part. And there's, my opinion, there's advantage to at least starting now because you can get a file to hold a place on the server, and then you can replace it later on. So I'll see you tomorrow at 9. Have a great afternoon. Looks like it's a beautiful day if you're in Lubbock, and I hope you can get some time and enjoy the beautiful day. Bye-bye.